Okay, let's take a look at section 11. We've been talking about matrix games. We discussed strictly determined games. Those are games that have saddle values. We've talked about games where one person has two strategies and we can use a graphical method. We know that in general games will have a mixed strategy, and now we complete the discussion by giving a general method for finding mixed strategies for matrix games with any number of strategies. Now, here it says a clue to the general technique may be found in the fact that the role player is a maximizing player while the column player is a minimizing player. It's the problems they're trying to solve sounds like dual linear programming problems. It certainly does. You have one person maximizing, one person minimizing, and they turn out to have the same answer. And in fact, this is exactly a special case of a dual linear program. Now here they talk about simplex method. In fact, you can use any solution method for linear programming problems to solve these games. I'll show you how to use an online solver. But what the important thing is to set this up as a linear program. And again, duality plays an important role because we do have one player maximizing and one player minimizing. All right. Well, let's go back for a moment to the earlier section where we first talked about setting up matrix games as a matrix. And we talked about mixed strategies for the role player, mixed strategies for the column player. The mixed strategy for the role player is a probability vector, meaning that it's a vector with non-negative entries whose sum is 1. And to get the value of the game for the role player, you multiply P times G, where P multiplies G on the left. So here we have this expression P naught G greater than or equal to VE. What does that mean? Well, let's take a look at the example down here. Here we have P naught G. In this case, P naught is 1, 0, and G is this matrix game. Now 1, 0 means that the role player always plays row 1 and never plays row 0. Now in this case, if we do this multiplication, we in fact pick out the first row in G, 50, 60. So the interpretation of 50, 60 is this 50 is the value of the game for the role player if the role player plays this strategy and the column player chooses column 1. This 60 is the value for the role player if the role player chooses this strategy and the column player chooses column 2. So in general, this P0G is giving you a row vector, and each entry in the row vector gives you the value of the game if the column player plays a different column. So there's going to be several different columns. Each different column will have a different value, but if this holds, then V is the minimum possible reward for the role player, minimum possible return for the role player. On the other hand, we have this similar situation here, GQ0. Well, there's an example down here. Suppose the column player always plays the first column, then his strategy is 1, 0. GQ0 will then be 50, 40, and that, in fact, if you take this matrix and multiply by this column vector, it's going to pull out the first column. This 50 is the result if the column player chooses this strategy and the role player chooses row 1. And this 40 is the result if the column player chooses this strategy and the role player chooses row 2. And again, this V has the interpretation of well, this is, in this case, it's a maximum result. Of course, we want the column player wants the result to be as small as possible. So this is you could say this is he's guaranteed to get at least a result at least as good as V, no matter what strategy the role player plays. Okay. So you can think of these in terms of a guaranteed worst results. If he plays this strategy, P0, the role player can't do worse than V. If the column player plays this strategy, Q0, he can't do worse than V. And if both row and column player play according to this strategy, they will both obtain the value V, which is the value of the game. Okay, so this short review about what the value of the game is and how that relates to these multiplications of row vectors and column vectors with the matrix of the game. So you see the importance of these equations. And these are just linear programming equations, right? This one is you have greater than or equal to constraints, and here you want to minimize, and here you have less than or equal to constraints, and here you want to maximize. Now the difference here between the problem that we have in the linear programming problem is that here we have a variable on the right-hand side, and typically before we have constraints, the constraints have been constant vectors without any variable. See, this V is the value of the game, which is unknown. So the way that we solve this, turns out, is that you divide both sides of the inequalities by V. And in order to do this, we need to make sure that V is positive. And one way of guaranteeing that the value of the game is positive is guaranteeing that all the entries of G is positive. All right. But as they point out in the chapter, this method will work as long as the value of the game is positive. We can divide both sides of this by V, and then we'll get an equation inequality for P0 over V, and then we'll do some fancy stuff to get the strategy that we need. So let's go back and see how that's done. So look at this equation here. This is very similar to the inequality we just looked at, P0G greater than or equal to VE. And again, the V is now gone, and instead of P0 we have Z. And it turns out that this Z functions like P0 divided by V. Okay. And once we solve for this Z, we'll be able to find P0 and V. And the dual problem, before we had GQ0 is less than or equal to F times V. Again, we divide both sides by V. The Q0 is gone, it now becomes X. We're going to solve for X and then recover Q0. So here we have a pair of dual linear problems. All right, because here, so just to show how it is a dual, here you're minimizing ZF, and we'll see in a moment why we want to do that. Basically, ZF is the sum of the entries of Z, because F is a vector of all ones. If you take a vector and take its inner product with a vector of all ones, you're going to get the sum of the entries in that vector Z. Similarly, this E is a vector of all ones, a row vector of all ones. If I multiply this by any column vector, that's going to give me the sum of the entries in X. Now, by the duality theorem, we can find optimal solutions to these two problems where the values ZF and EX agree. So in his case, he's saying Z0 is the optimal solution for the minimization problem. X0 is the optimal solution for the maximization problem. Duality theorem says that these two values are the same. Okay. So at this point we can recover our P0 and Q0. Remember, P0 and Q0 are our mixed strategies. They have to be probability vectors. So what you do is you take your Z0, which you obtained when you minimized this problem, and divide by T, which is the value, the minimized value. Now, if I take Z0 and divide by T, I get a vector. Is this a probability vector? The answer is yes. If I take the t equals z0f and divide both sides by t, I'll get 1 equals z0 over t times f. 1 equals z0 over t times f. Now z0 over t times f is simply the sum of the entries of z0 over t. The sum of the entries of z0 over t is 1, and that's exactly what it means for z0 over t to be a probability vector. Okay? Similarly, I can take this equation t equals ex0 and divide both sides by t, and that will give me 1 equals e times x0 over t. Now, e times x0 over t is simply the sum of the entries of x0 over t, which means that x0 over t is a probability vector. All right, then finally we take, it turns out that the value of the game is not this value of t, which was the value for our optimization problem, but it's 1 over t. How do you see that? Well, take this condition here and divide both sides by t. Then we get z over t times g is greater than or equal to e over t. All right, I've typed it out here so you can see it. I just took this equation and divided both, this inequality rather, and divided both sides by t. Now, what does this show me? Here I have my probability vector, z over t is equal to p, and I multiply by g, and I get 1 over t times e. On the other hand, if I multiply both sides, I should actually make this a z0, because that was the optimal here. I'll make that z0. Right. I can also divide both sides of this inequality by t, and I'll get, well, here with x0, we'll get g times x0 over t is less than or equal to 1 over t times f. Now, if you look back at the previous chapter that we just reviewed before talking about this, this is exactly the condition for 1 over t to be the value of this game. 1 over t is a guaranteed return for the role player if he plays the strategy z0 over t. And 1 over t is also the guaranteed return for the column player if he plays the strategy x0 over t. All right? So our strategy has worked, and we now have a mixed strategies for both the role player and the column player, and we also have the value. All right, so let's see how this works in practice. So here's an example of a game. This game was obtained from the matching pennies game. The matching pennies game has 1, minus 1, minus 1, 1. And in order to make this game have a positive value, we just add 2 to each entry. If we want the value of the original game, we'll just subtract 2 from the result that we get here. Okay, this game is not strictly determined, so let's go ahead and set up our linear programming problem. Right? So what's the linear programming problem going to be? Let's take this one first. This one says I want to maximize EX, that's actually the sum of the entries of X, subject to these constraints, gx less than or equal to f. And f, remember, is the vector with all ones. All right? So how does that work for this one here? If I have this matrix 3, 1, 1, 3. Well, this is my g, and I want to multiply g times x, and that should be greater than or equal to f, which is the vector of ones. Right? So let me go ahead and get a solver, and we can do this. You can find the solver at this site, phpsimplex.com, and just click here. And I'm not sure why it's showing in Spanish, I switched it to English. I think it's because I was accessing this from out of the country. So we don't need to worry about the method. But how many decision variables? Well, we have a 2 by 2 matrix, so there are 2 decision variables, the x1 and x2, and there are 2 constraints. Right. All right, now remember what the optimization problem is. Let me go back here. Here's our matrix, and our 2 variables are x1 and x2. And if you remember what we want to do, the problem is this one here. Gx less than or equal to f. F is the column vector of all ones, and I want to maximize the sum of x1 plus x2. Well, let's go back and see if we can do this. We want to maximize 1 times x1 plus 1 times x2. And my coefficients were from the matrix here. If you remember what the matrix here was, it was 3, 1, 1, 2, 3, 1, 1, 3. So my first constraint is 3x1 plus 1x2. Less than or equal to is correct, and this should be a 1. This one, second one, corresponds to the second row of the matrix, 1x1 plus 3x2 less than or equal to 1 also. So you can continue. And then here let's see. Let me go down here. Oops, sorry. All right, so you can check that you have your correct, form of the equation. We'll continue here. And this is the simplex method. I don't want to show the whole simplex method. I just want to show the result. So let me go back. Should just be go to direct solution. And here's my solution. x1 equal 0.25 and x2 equal 0.25. And the optimal solution value is z equals 0.5. So to get my result, as it shows in the book, is that you have to divide these here by this optimal solution value, which would give me 0.5, 0.5, and that's my optimal column strategy. And the value of the game is 1 over this, which is going to be 2. All right. So I solved the I solved the column strategy problem. To solve the row strategy problem, we have to solve for, let's go back and just get that equation. Zg greater than or equal to E. And this is a minimization problem. So I'm going to minimize the sum of the z's such that zg is greater than or equal to E. Now zg means I take z1, z2 multiplied by the columns of g. Well, let's go back to my PHP simplex and see how to make that work. Okay. All right, so in this case I have a minimization problem. I'm still minimizing the sum. I can't change the x's here to z's, but you should be thinking z's. And if you work it out, in this case, the column, the multiplication, the row vector times the columns of my game matrix is going to give me a greater than or equal to here and a greater than or equal to here. You can continue, and my solution is correct here, so let's just do the direct solution. And here also I get half-half. So the value of the game is going to be 1 over this value, which is 2, and my optimal solution is going to be these two values divided by the z, so it's also going to be 0.25 over 0.5, which is 1/2, 0.25 over 0.5, which is 1/2. All right. So that should give you some idea how to solve these problems using an online solver. You can use another online solver if you wish.